recording. So yeah, just a heads up to everyone. Workbook number 6 will be due next Monday at 11:59 p.m. It'll pretty much work the same way as last Monday, a few days ago, worked. I'll just use the Monday class period to talk about the workbook assignment. I do encourage you to work on the problems ahead of time if you can, and then just check them with what I have. It's a good way to see where you might be going wrong at, which might help you for your test later on. But yeah, that'll be due next Monday, workbook number 6. So besides for that, just keep in mind that graphs of rational functions is due on the 14th. And on Friday's class session, when the tutors help you all, that corresponding homework will be due on the 16th. So you should go ahead and start watching or watch that video at some point on polynomial and rational inequalities, which is already up under lecture links, which can be found here. So just a heads up to everyone. So besides for that, does anyone have any specific homework questions? Or if not, I'm just going to go through ones that I haven't covered in the video. So if nobody has any questions about specific ones, you can go ahead and start. And you can ask me at any time. That's no problem. So graphs of rational functions. Again, the homework is due tonight. So as you go through some of these, find the intercepts. I trust you can find intercepts by now. The type of asymptote that'll never intersect the graph of a rational function. I talked about that. I've talked about that in the video. Y-intercept, hopefully you can figure out the y-intercept by now. And then this is where we get to the main substance of this section. It's not very appealing, I'm not gonna lie. It's 12 parts in total, which is why I want to focus on these problems. I did do a problem very similar to this. So in my notes, the first problem I do is similar to number 4 in the homework. So I'm going to skip that one, and I'm going to start off by looking at this problem right here. Or rather, let me clear it out and get a new problem. So I'm going to go ahead and start from 5x plus 5 divided by 3x plus 12. And just talk through the steps and explain the motivation behind it all. So let's start off. 5x plus 5 divided by 3x plus 12. So that was, I think, number 5. Make sure I wrote that down right. 5x plus 5, 3x plus 12. And we have to write the given function as a single rational expression and then factor the numerator and the denominator. Okay, so that's the first rule. It wants us to first write it as a single rational function, which means a single fraction, which it's already in. So that part's already okay. So we're going to ignore that, and then it says to factor. So part A primarily says to factor the rational expression. And to factor a rational, that's equivalent to factoring the polynomials in the top and the bottom of the rational function. So really what's going on here So you might notice in the numerator, both terms have a 5 in common, so we can factor out the 5. And in the denominator, both terms have a 3 in common, so they will require you to factor out even numbers. So when you factor out a 3, you're left with x plus 4. And if you wanted to check to make sure you factored out correctly, you can always distribute back in. But this would be the factored form here. And then it goes on to ask for the domain. Now remember, the domain of a rational function, it means you set the denominator, just the denominator. Notice the numerator is not a part of this. The denominator not equal to 0, and you solve for x. So that's pretty easy. Just move 12 over, divide both sides by 3, and we get that x cannot equal -4. So that's the domain. So that part starts off fine. So we're going to look for the option that says x cannot equal. So notice the not equal sign down here. That's why I'm going to use this one. And then it says to write the function in lowest terms. But what that means by lowest terms is if there's any cancellations, then please go ahead and cancel. So if there's anything similar in the top and the bottom, we could cancel those out, which is why the factorization step was so, that's why the factorization step was asked for in the beginning. So we can look at the factored form and see, is there anything the same in the top as in the bottom? And if so, we can cancel them out and simplify this, but there's not. It's already in lowest terms. So it's already in lowest terms. There's nothing in the numerator that's equivalent to the denominator that we could cancel out. Everything's different. So it's already in lowest terms. And now it wants us to find the x and the y intercepts. So let's go ahead and find both of those one at a time. So I think this is actually part, no, we'll call it part C. Why not? So we're going to find the intercepts. So there's the x-intercept, which means we set y equal to 0. And so when we do that, remember the original function was the 5x plus 5 divided by 3x plus 12. So now we're setting that equal to 0. So we're setting the whole function equal to 0, and we're solving for x. Now we can cross multiply because this is a rational function. So we can cross multiply, or equivalently multiply both sides by the least common denominator, which would give us 0 times 3x plus 12 is equal to 5x plus 5. But 0 times anything is 0, which is why this simplifies very nicely. And from here, we can solve for x pretty quickly. So if anything, we have an x-intercept of -1. And equivalently, we can go ahead and figure out the y-intercept. Which the y-intercept is normally easier to find. You replace every x with 0. It simplifies very nicely to really just 5/12. So we get an x-intercept of -1 and a y-intercept of 5/12, it looks like. So let's go ahead and plug those in. And it says type integers or fractions, so we're just going to type in, like I said, -1 and 5/12. So those are the answers. Notice I'm putting -1 next to x-intercept, 5/12 next to y-intercept. So what it goes on to say, now that we have in particular the x-intercepts, which are much more important in the situation, the x-intercepts, then we need to determine the behavior at all the x-intercepts, which we only have one. So it's nothing too crazy. And we're trying to determine whether the graph will cross or touch. So we're going back to this idea of crossing or touching. And to figure that out, so the value, the x-intercept that we have is x is equal to -1. And so the question is, does it cross or touch? So that means we need to find which factor this number came from. In the section on polynomials, the factors that we had, we could just check the exponents of those and know exactly whether something crosses or touches. For -1, we need to figure out which factor it's coming from. And this is a little bit trickier because rational functions, the factors happen in the numerator and the denominator. So really, this is a factor, the 5x plus 5, and this is a factor, the 3x plus 12. So the question is, where did the -1 come from? The numerator factor or the denominator factor? And the answer is it comes from the numerator one. Because notice what we solved for to figure out -1. That is the numerator. We ultimately set the numerator equal to 0. So this comes from, it comes from the factor 5x plus 5. Now that whole factor, what exponent is that factor being raised to? Well, you might think there isn't an exponent, and you're exactly right. The exponent is understood to be 1. This factor has exponent, i.e. multiplicity, you might recognize that word, of 1. So what does that mean? Since the multiplicity is odd, because one is an odd number, you choose crossing or crosses. That is the thought process, and I've now just detailed the thought process step by step, the exact way you should think about this problem. So if anything, I want to pick cross. Anything that talks about touch would not be, relevant here. So just simply cross. And what was the value in question? It was -1. I'm choosing the graph will cross at x is equal to -1 because that was the x-intercept. All right, we'll move on to the vertical asymptotes. We move on to the vertical asymptotes. So this was, you want to think about this as part D for the crossing and touching aspect. Part E, we can call it. The vertical asymptote. So I mentioned this in the Monday session when I was going over the workbook assignment. The vertical asymptote is almost 100% of the time just the domain, but with a slight variation, a very slight variation. So what was the domain? The domain we found as, let me see it over here, x is not equal to -4. So if we, so x is not equal to -4. So that is exactly what I'm going to write down here for the vertical asymptote, except I'm going to put equals -4. Notice all I did was change from a not equal sign to an equal sign, and that's it. That's all I did. And I'll explain, hopefully I'll get to a problem that explains when this doesn't happen. But the majority of the time, your domain will simply carry over to your vertical asymptote. There are exceptions though, but most of the time this is a good, in case you're just unsure. And so notice it says type an equation. It does say type an equation. So that means you have to, when you type an equation, it means you need to have an equal sign somewhere. So you have to have an equal sign somewhere. So I said x is equal to -4. Notice I am typing out an equation and not just simply -4. And I'm putting it in this first blank up here because we only found one vertical asymptote, just one. Okay, so now we need to figure out the behavior on either side of the vertical asymptote. And the way we do this so remember, a vertical asymptote, just in general, if there's a vertical asymptote somewhere, it would look like this. And the graph has to trace the asymptote in some way. So either the graph will trace the asymptote going upwards forever, or it'll trace it going downwards forever. And what this problem wants us to figure out is which direction is it? How do we determine that is really the question here. And so there might be a few different ways of determining this. I think we're starting off with, okay, so it's asking what's happening on both sides of this asymptote. So the left side and the right side, do they both go upwards? Do they both go downwards? Or do they alternate? So that's the 4 potential options. And so the asymptote well, we have the asymptote written up here. So we'll start off with behavior to the left of x is equal to -4. So the way I like to think about this is I pick a number that's to the left of x is equal to -4, that is kind of close to -4, and go from there. So what's a small a number that's really close to -4 that's to the right of -4? If we choose x is equal to -4.1, that is to the left of -4. If we choose this value here, plug into the function. Now, the reason I'm choosing a number fairly close is because I want to see if this number gives us a positive value, or a really large positive value, or a really low negative value. This will give us an idea as to whether the graph is going upwards or downwards. So the function that we had was the 5x plus 5 over 3x plus 12. So what we're now going to do is we are going to plug in 4.1 in for every x value and see what we get. So I'm just going to rewrite the function. And it's okay to have decimal approximations. We are just looking for the number. So I like to do the numerator and the denominator separately. Actually, let me check something right fast. We might have to pick a different point. I'll explain why. Oh, I'm sorry. I'm so sorry. This is that's not right. I'm supposed to plug in -4.1. I'm sorry about that. See, I put positive 4.1. I was wondering why it was not coming out the way I was expecting. But I said to plug in -4.1. So my fault. -4.1. -4.1. And so we get a fairly large positive value. And so what this tells us is that we can expect this to go towards positive infinity. So that's sort of the thought process there. We pick a number very close to the asymptote. So this is what we're doing here. this is the motivation for this process. So for x is the intercept at, or sorry, the asymptote at x is equal to -4, what we're doing is we're picking a number about right here, fairly close, -4.1. And the reason why we pick close is because we want to see whether the graph, we're trying to get a snapshot of the graph, whether it's going upwards or downwards. And by figuring out that it is upwards, it gives us a pretty good indication that the graph is going to go in this trend up here. So that's what we're doing. We're trying to find a little snapshot of the graph. And so by determining whether it's a large positive number or a small negative number, or a large negative number rather, but we're trying to see which trend this is going in. And that's what we're trying to figure out, whether it's going to positive infinity or negative infinity. And so normally I pick a number that's 1/10 of the way in either direction. So here we started off with behavior to the left, which is we found to be positive infinity. And now we can look at behavior to the right. So normally I like to, again, pick a number that's 1/10 of a value away. So taking -4 and looking at it to the right slightly, adding 1/10 to it would give us -3.9, and plug into the function. Oops. So we're going to do the same thing as before. Let's see what we get. And so from here, we seem to get a larger negative value, which means we would have negative infinity. Just negative equates to negative. And so these numbers that I'm choosing, the 4.1 and the -4.1 rather, and the -3.9, these are numbers that are 1/10 of a value. So they're fairly close from the asymptote that we are checking. And this is my way of doing it. So what we have found in essence so this is what we have found. For the asymptote of -4, we found that on the left, when we chose the -4.1, the graph is going towards positive infinity, while on the right, the graph will be going towards negative infinity. So this is what we've found. So it gives us an idea of the behavior of the graph near the asymptote. So we're not going to pick choice A because choice A is implying that we have two asymptotes because we have two blinks. So we don't have two, we have one. Part B is saying that both of them will go up or both of the sides will go down to either positive infinity or negative infinity. So that's not the case. In this case, they alternate. infinity on one side and negative infinity on the other side. That's what we have found. And so from here, we can go ahead and determine the horizontal asymptote. So we are on number choice, or next one, part G. So the horizontal asymptote. So hopefully you remember by now the conditions of how to determine the horizontal asymptote. That's the one that has the three various conditions dealing with the degree of the numerator and denominator. So what we had was 5x plus 5 over 3x plus 12 plus 12. And the degrees of these are both 1. So remember, that's the highest exponent of the variables. So with the degrees being the same, the horizontal asymptote, remember, is the ratio of the leading coefficients. So remember, ratio is fraction, leading coefficients, numbers in the front. So it's 5 over 3. And generally, this is represented as y is equal to that number. Normally, it's an equation, because the horizontal asymptote is a line, and we can give an equation to a line. How do we equate it? Slope-intercept form, and there's no slope. So even notice here, it says type an equation. Y is equal to 5 divided by 3. And generally, we're not going to have an oblique asymptote. You could just get used to this for every problem. They're not going to come up in this class. So no oblique asymptote that I've ever seen. So you could just keep pressing. No oblique asymptote. And so additionally, we figure out which points, because technically you can intersect a horizontal asymptote, which may seem strange considering we describe asymptotes as these boundaries that you cannot cross through or touch, but horizontal asymptotes, you can cross through them. It's the vertical ones you cannot cross through, as I mentioned in the video. But so here, what we need to do is figure out, well, which values does the graph intersect the horizontal asymptote at? And so to figure that out, oops. We set the function equal to the horizontal asymptote in question. Notice we are setting the function equal to the horizontal asymptote that we found, and whichever x value we find, that would be where the graph would intersect, would potentially intersect the horizontal asymptote. So we can cross multiply. to get 5 times 3x plus 12 is equal to 3 times 5x plus 5, which we can go ahead and distribute. But something interesting that happens here, the 15x's cancel. And we just get that 60 is equal to 15, which doesn't make any sense. Since this does not make sense, because there's no more x values, there's nothing to solve for, which means we do not intersect the horizontal asymptote at all. So that would be our conclusion. So additionally, we need to figure out where the graph is below the x-axis. So it says here, use the real zeros, which are the x-intercepts of the numerator and the denominator, we'll talk about that in a bit, to divide the x-axis into intervals and using something called the number line test. So what we're trying to do is determine where the graph is below or above the x-axis. So we're trying to figure out whether the graph is happening below or above the x-axis. And so what it's wanting us to do, and this actually is an introduction to things that we'll see in the next section on polynomial and rational inequalities. We'll do a process very similar to this. We're figuring out what's above or below the x-axis. And so to determine this, what we need to do is figure out the real zeros, or the zeros from the numerator and the denominator, it says. So in other words, if we were to split this up into the numerator and the denominator separately, then what would the zero of each one of those factors be? Which means we can solve for both of them. So we get -1 and -4. Those are the zeros that correspond to the numerator and the denominator, respectively. And from here, what it's saying is now we're going to use a number line test. So in order to have a number line test, we need a number line. And so from here, what it's saying is we've now split the interval into 3 sections. A section here, a section here, and a section here. And we're going to choose a random point from each one of those sections. So see, -5 comes from this section, -2 comes from that section, and 0 comes from this section. I chose random points from each one of those sections. The -5 is just any number that's less than -4. -2 is in between -4 and -1, and 0 is greater than -1. And so what this problem wants us to do is for each one of these test values, is what they're ultimately referred to as, we want to plug them into the function and see whether we get a positive or a negative value. So we're just going to plug in 5 times -5 plus 5 over 3 times -5 plus 12. So plug in this one in first. Or rather, we get a positive value. So that tells us that everything to the left of -4 is going to be above the x-axis. That's what this tells us. And so we can do the same thing for -2. So what is that? That's -5, 6. So here we get a negative number, which tells us that on the part of the graph in between -4 and -1, everything's going to be below the x-axis. And finally, we can plug in 0 and see what happens. Which is a positive value. So this tells us the characteristic of the graph, whether it's happening above the x-axis or below the x-axis. So since we have stuff above the x-axis and below the x-axis, I'm going to use answer choice C here because it has a blank for above and a blank for below. Now, once the answer is in interval notation, so the intervals here -infinity to -4 and -1 to infinity. It's referring to that segment there where we have a positive symbol, which means above, and then additionally over here, but not in the middle. And then additionally, we found that below the x-axis, it's in between -4 and -1. And in fact, I just realized that -1 should have a bracket next to it because -1 is included in the graph. But -4 should not because there was an asymptote there. Wait, I'm sorry. I'm thinking to another section. Just ignore what I said. I don't know why I said that. That should just be parentheses. I'm thinking ahead. Those should be parentheses. So below from -4 to -1. And finally, we can choose the correct graph. Now, one of the easier aspects of determining the correct graph is by viewing what the asymptotes are doing. So over here, the vertical asymptote is to the left, and the horizontal asymptote is going down, as opposed to this one where the horizontal asymptote is going up, but the vertical one's going to the left. Or left relative to how you were all seeing it might be this way. So we found the horizontal asymptote as a positive number and the vertical asymptote as a negative number. So the vertical asymptote was -4, and the horizontal asymptote's a positive number, which means it should go to the left and up. Actually, this seems to be the only one that goes to the left and up. So notice here's the vertical asymptote at -4. And we said that the horizontal asymptote was 5/3. So 5/3 is roughly 1.67. So notice there's a horizontal asymptote here right underneath 2, i.e. 1.67. So that's how you would do this problem. Does anyone have any questions about this problem or have any specific problems you want me to do? I'll just choose another one. So if not, I'll go ahead and find another one. Yeah, I think I want to do, let's see. I think I want to do problem 9 here. Unless anyone's opposed to me doing problem 9. I think I'm going to do problem 9. So if not, all right, let me go ahead and do that one. So hopefully you all have this written down, and if not, you can check the video that I put up for this. Okay, we'll move on to problem 9, which is 10 divided by x minus 2, x squared minus 100. Well, and it starts off by asking us to put this into a single rational expression and then factor the numerator and the denominator. So you might think, all right, well, they already factored the problem for us. And the answer is, well, not quite. They partially factored the denominator for us. Of course, the numerator is fine. It's just 10. So the denominator is not fully factored because the x squared minus 100 is a difference of two squares. And so hopefully by now you know or remember that what this equates to, as I'll write momentarily here, so x minus 2 stays the same. That should be fine. But the difference of two squares tells us it would be x plus 10, x minus 10. And the reason I'm using 10 is because that is the square root of 100. So that is the difference of two squares, because 100 is a perfect square. So that is the true factored form for this problem. That's the factored form. Now they ask us for the domain. So the domain here, remember we set the denominator not equal to 0. And we solve for x. But since this is factored, this is equivalent to finding the zeros, which means we can find the x values very quickly. So positive 2, negative 10, and positive 10. That would represent our domain. Now those are three x values that x cannot equal, because we did have a not equal sign. So we are going to choose answer choice C, which has the not equal sign. So we can go ahead and jot those down. It also goes ahead and wants us to put this into lowest terms via any cancellations we might have, but there's no equivalent expressions going on in the numerator and the denominator simultaneously. So there's nothing to cancel. So it's already in lowest terms. So we can go ahead and figure out the intercepts again. Start off with the x-intercept. Oops. Which means we set y equal to 0. But the convenient thing for us is whenever we cross multiply here, virtually everything will cancel out. So when we cross multiply, what we end up obtaining is 0 times that whole denominator, which is just 0. Really, we just get 0 is equal to 10 after we cross multiply, which doesn't make any sense. So thankfully, we get no x-intercepts, which is actually going to simplify this problem pretty nicely, as we'll see later on. We will probably get a y-intercept, though. So that was the first one, the x-intercept. Let's move on to the y-intercept. set x equal to 0. So now this is going to be 10 divided by 0 minus 2, 0 plus 10, 0 minus 10. So that's the same thing as 10 divided by negative 2 times 10 times negative 10. It's 10 divided by 200, 1 over 20. It's 10 divided by 200, so it's 1 over 20. So that's it. Because they want a simplified fraction. So there's no x-intercepts, and there's one y-intercept of 1 over 20. Okay, so we're going to pick answer choice B because it has the no x-intercept option, and the y-intercept we found was 1 over 20. So now we need to figure out the behavior near any x-intercepts. But guess what? We didn't find any x-intercepts. So guess what we get to skip? So not too bad, because we did not find any x-intercepts. There's no x-intercepts, but we have a bunch of vertical asymptotes. So the vertical asymptotes So remember, the vertical asymptotes is generally you take whatever the domain is, and you just, for mostly all the problems, you take whatever the domain is, and you change the not equal sign to an equal sign. So before we said that the domain, the domain was x cannot equal all those things, so the vertical asymptote, x will equal all those things. So we're going to choose the option that allows for 3 vertical asymptotes, because we have 3 of them. And it wants the leftmost, the middle, and the rightmost, which just means put them in order. The leftmost is the smallest one, which is negative 10. We move on to 2, and then finally 10. Oh, got to type in equations. Sorry. X is equal to, as you can see, I do it too. So just a nitpick. So those are the 3 asymptotes. Now, unfortunately, that means we need to find the behavior on the sides of the vertical asymptotes. And so what we're going to do, we're going to be plugging in a lot of numbers here for each one. So this is the behavior around asymptotes. Well, in particular, vertical asymptotes. And so we have 3 asymptotes, so that means we have 3 different things to determine. So the first asymptote we found, the vertical asymptote, was x is equal to 2, which means to the left of 2, we would have to pick 1.9, and to the right, we'd have to pick 2.1. Those would be the numbers that we would plug in for x. And really, I'm going to pick, actually, I'll just go ahead and plug it in as is. So if you plug all of this in, it's to 1.9 plus 10, 1.9 minus 10. Okay, so interestingly enough, we get 1.037, which is positive. Okay, that's interesting. And then the next one we should get 2.1 minus 2. What else is there? There, 2.1 minus. So 10 divided by 2.1 minus 2. 2.1 plus 10, 2.1 minus 10. So we get a negative number. So that means on the left, we'll get positive infinity, and on the right, we'll get negative infinity. Okay, so that tells us for x is equal to 2, that on the left side of that asymptote, it will approach infinity, and on the right side, it'll approach negative infinity. And we'll end up, and just for the sake of time, you'll end up getting these same things for the other two. And you can tell this via, if you're comfortable with multiplicities, there is an easier way of determining all of this. The multiplicity of each one of those numbers is 1, which still corresponds to asymptotes. It just means that you will always flip your infinities. If you are interested in that multiplicity-esque way of thinking about it, just email me. Some people don't like it, some people do. So just let me know if that sounds interesting. If you're good with multiplicities, then yeah, there is an easier way to check the behavior. Oops. So really, the answer we are going to provide is really all of them right here. They all alternate. I mean, roughly the thought process I was referring to was, since the multiplicity of 2, 10, and -10 are all 1, even though these are asymptotes, the infinities will cross or alternate. So it's an interesting generalization to the idea of multiplicities. So from there, let's go ahead and find the horizontal asymptotes. So remember, this has to do with the degree of the numerator and the denominator. So the degree, so the problem in question is here, the degree of the numerator is 0 because there's no variable. The degree of the denominator, though, is 3. And you could figure that out using term domination. You would have 3 x's that all multiply together, and you would have x to the third. So since the degree of the numerator is smaller, then we need to, we'll go ahead and say that the horizontal asymptote is y is equal to 0. That's whenever the denominator is larger in terms of degree. It's always 0 in that case. And there's never an oblique asymptote. You don't have to worry about that one. So horizontal asymptote, y is equal to 0. No oblique asymptote ever. So that one should be a quick one. So now we need to figure out where the graph could potentially intersect the horizontal asymptote, which means we would set the whole function equal to the horizontal asymptote, just like this. But this might look familiar to you. We did the same exact thing whenever we found the x-intercept. We've already done this computation already. And what happened? What ended up happening was we found that 0 was equal to 10, which didn't make any sense. So there's no point of intersection. So finally, we need to do the number line test, which is also where that idea of multiplicity comes into play. So let's, in fact, let me go ahead and explore that idea of multiplicity, like I mentioned before. Because if so, it'll simplify a lot of these behavior problems. So this is saying to use the number line test. And so it says use the zeros of the original expression. For the numerator, it's obviously none because there's no x values. For the denominator, it's the 3 that we had before, 2, -10, and 10, which tells us what we need to put on the number line in question. We're going to put them in order. So -10 over here, 2 in the middle, 10 over here. Now from here, we know what the behavior, or we would need to figure out the behavior of just one side only. That's all we need to do in order to use the multiplicity trick. Now notice the multiplicity for each one of these. I'm going to draw this in blue. 1, 1, and 1. That means that at each one of these asymptotes, it will cross, which I put cross in quotes because these are asymptotes. We're not really interacting with them too much. And we're not crossing through them, but what that means is that, so at asymptotes, you approach either infinity or negative infinity. What crossing tells you is that you will constantly alternate between which infinity. Positive infinity on one side, automatically to negative infinity on the other. Or if you're on negative infinity on one side, you alternate to positive infinity. So the ones that we figured out, and we actually did 2 of these by hand for 2 here. So let's scroll up a little bit. We figured out to the left of 2, it's approaching positive infinity. So to the left of 2, we are approaching positive infinity. And additionally, to the right of 2, we figured out it's approaching negative infinity. And since all of these multiplicities are odd numbers, and every time we cross around, these will always alternate. That's what this means. If any of them said touching, then we would, so if 2, for example, had an even multiplicity, then to the left of 2 and to the right of 2, they would both be either both positive or both negative. They would not alternate. It would just repeat. So that's a cool way of using the multiplicities to save you a lot of work. So notice I did no work other than just that. So I wanted to show that option as well, and also hurry up and finish the problem since I'm running low on time. So I'm going to just go ahead and put the answers straight into the homework here. It's above the x-axis from -10 to +2, and from 10 to infinity. And it seems to be below from negative infinity to -10, and from 2 to 10. I'm reading all of this off of the number line. Just reading it off the number line wherever the positive values are at, wherever the negative values are at. Since all of the values alternate between positive and negative infinity, choices like B would not be correct because some of the options we had go to positive infinity. But for B, everything seems to just be below the x-axis, and we already proved there's stuff above the x-axis. So B and D would both be out because they're both one-sided, and we've shown many times over that this is two-sided, and it turns out that we will choose answer choice C because with C, the rightmost part is above the x-axis, which agrees with our determination over here. So I am out of time. That's all I have for today. So have a good day. Homework's due tonight.